So we've defined equilibrium and shown you how to work out the equilibrium constant using the equilibrium expression. And now we're going to look at the different stresses that you apply that can push the equilibrium to the left or to the right. Now, this is called the Chatelier's principle. So if a stress is applied to a system in dynamic equilibrium, the system changes partially to relieve the stress. So basically, if you increase the left-hand side, it'll move to the right-hand side. Or if you decrease the left-hand side, it'll move to the left-hand side. So I've just done a picture like that. So if you increase that, it goes to there. And all the other combinations. So if you increase this one, it goes to here. If you decrease this one, it goes to here. And if you decrease the other side, it goes to there. So it's all trying to even itself out. Okay, so if you're adding A, will cause A and B to turn into more C and D, and decreasing A will cause C and D to turn into more A and B. Okay, so the first one is concentration. So that's hopefully the easiest one. So you can see from the graph here that there's been a spike, and so this one has increased. So Le Chatelier's principle means to relieve the stress, that'll make this one increase. So you should see these two now drop slightly and this one increase slightly. And so you can see they then drop slightly and the other one increases slightly. Okay, so we say that the reaction is pushed to the left-hand side. The next one is pressure. Now, pressure is the only, is changing the concentrations here. So if the pressure is increased, the reaction will shift to the side with the least number of moles of gas. So you've got 4 moles of gas here and 2 moles. And what we're doing here in this one is we're increasing the pressure. We're not worrying about temperature for the moment. And if we increase the pressure, we're increasing the amount of ammonia, and that's the products, which makes sense. So it's increasing the pressure, pushing it to the side with the least moles of gas. And so we're moving it to the right-hand side. Now we are permanently changing the concentrations here. So you would think that the Kc would change. The Kc actually remains constant. And that's because of the way the equation is set up to account for those changes. So there's a video on the website that goes into that in a bit more detail. It is very detailed, so it's never asked. But if you're curious, I've explained it. Some teachers use partial pressure, but I've just used the equation and subbed with some numbers to make it simpler to explain it. The next one is a catalyst. They normally ignore this one because catalyst, we'll say, has no effect, but it actually has an effect in making the equilibrium occur faster, so reaching equilibrium faster. So you're lowering the activation energy. It's easier to go left and right, but it happens quicker. And so if you have a careful look, you should see that this reaction thing, sort of rate of reaction curve, is much, much quicker, and it gets to equilibrium much, much faster. Onto temperature now. So just be aware that if it's positive, that's endo. If it's negative, it's exo. And so the easiest thing to do is to work out whether it's endo or exo and write it on the correct side. And then you know if they're adding or minusing, you can just write it on top of the heat. And so for this one here, you can see that this one, PL3, has gone down. PL, that's a 5 down there. That's a 5. That one's gone down. And these two products have gone up. So I can, without reading this, adding heat, you can tell that this heat must have been added so that the stress is going to this side. So these that's going down, these are going up, and they're gradual. Okay, so that's the easiest way to work out what's going on with that. And so you will say the equilibrium is pushing to the right-hand side. Now, this is the only one, that's a permanent change, the only one that is actually changing the Kc. And so this is how I like to explain it. I like to realize that this is heat energy being absorbed and stored as chemical energy, and the favorable one is obviously chemical energy being lost, enthalpy loss to heat energy and loss to the environment. And so what happens if you increase the temperature is you make more heat available to be converted. And so it's easier for A to convert to B, and so the A drops and the B increases, which means the K will go up. Okay, you can also write it like this and think, oh, okay, well, if we're increasing heat, we're pushing it to this side, so A will go down and B will go up. and therefore the Kc, products over reactants, will go up, and vice versa for the other way as well. Okay, so kind of two ways to explain it there. Now, if you get an equilibrium graph, have a careful look to work out what's going on with the equilibrium graph. If only one thing goes up or down, it's removed or taken away or added to the system. This one's added, and then check the equation to see if it makes sense that the correct things go up and down, and also check the ratios. The ratios should be the same as well. Okay, they should go up in the correct ratios as up or down. Now, if everything goes up or everything goes down, especially if it's a gas, that indicates like a sudden decrease in volume or increase in volume of the container. So that's a pressure change. And so the concentrations are all instantaneously changed as well. If they're all gradual, it's suspicious that there's been a temperature change, and you can confirm that by doing grabbing all these values off the graph and doing a Kc check before and after to see if the Kc values have changed. Okay, so that's pretty nasty. And if they're going to be super nasty, you should also check how long it takes to reach equilibrium. And if it's a shorter distance, it's suspicious, or longer, that it's a adding or taking away of a catalyst. Okay, so as a summary then, if you increase the concentration, it will shift, increase the concentration, shifts to the opposite side. Decrease the concentration, it'll shift to the side that decreased the concentration. Kc doesn't change, it'll stay the same. If you increase the pressure, where's my pen? It'll shift to the side with the least moles of gas, decrease pressure to the most side of gas. Kc doesn't change, explanation on the website. Extra information not needed. Increasing temperature shifts to the endothermic side. So let's just make that heat equilibrium. So increasing temperature shifts to the endothermic side. That's endothermic side. Decreasing temperature, the exothermic side. So that's correct. And we know Kc changes. For that, the equation doesn't account for that, but it does account for gases. And adding a catalyst is no effect. These are taken from a textbook, I think. That does have an effect. Equilibrium is reached faster. I will change that and fix it. All right, the PowerPoint slides are on the website. Kc doesn't change, okay?